Jason Weston from Google, New York. Okay, he is originally from the UK, but has worked in the US in various labs over the last 10 years, and worked in Germany for a while as well, Tübingen. You may know him for his machine learning work, and this applies to all of us throughout the three projects and the other people who are not actually in the workshop. So, Jason.
Hello everyone. I met some of you just this morning, and yeah, it appears there's a lot of people working on Steve, which I haven't actually worked on. So Jason Eisner actually contacted me to give this talk, and he told me try to talk about some stuff on text and some stuff on images. That doesn't actually, so that's what I'm going to do. It doesn't actually include any speech, but I thought it was covering several bases, but maybe not enough. But that's what you're going to get. And yes, it's actually kind of like two talks in one. There's a bit about text and a bit about images. And they're both using the same, basically, family of algorithms, which is this kind of supervised learning to rank, which learns an embedding of words or images. So you learn these hidden representations, but specifically to optimize the loss function that you're interested in. So with, in a supervised fashion, supervised training data. So yeah, so the first part is going to be doing that for text document retrieval, and then the second part will be for labeling images with text, so image annotation. And yeah, so in particular, I mean, kind of the first part was something I worked on before the second part, so it's kind of chronological, and so the second part includes some kind of improvements, basically, but I haven't actually gone back and applied them to text. So in the first part, I'm going to be optimizing like AUC kind of measures, which isn't really exactly what you want to do. And in the second part, I'm going to be showing how to use the same kind of algorithm to optimize precision K measures, like the top of the rank list, which is actually more like what you want to do. So as we go through the two talks, you'll see that improvement. But starting from the first part, as my collaborators listed there, Big Bai, Eric Rocher, Kunimiku, Master, and Yanjun Ki are all at NEC, and Corinne Cortez and Marielle Murray at Google. Because some of his work was at NEC, and I kind of continued it at Google, basically. So the goal of this this part of the talk is to basically, you've got a query, a text query, and some text documents, and you want to learn how to match them. Okay, so it's a classic retrieval problem. And in particular here, the key point of this first sentence is the learn. I want to learn how to do that, because it means the simplest baselines don't really have any learning, right? If you just use like vector space models that just take a bag of words of the document and a bag of words of the query, and just kind of like count the number of matches, maybe weighted by some kind of frequencies. That would be your kind of baseline. It doesn't have any learning. So we want to be able to learn how to do better than that, at least. And there's obviously been work in this area. There's been kind of these like learning to rank approaches by Weston, Eames, and Chris Burgess, and many others that typically use hand-coded features, like a small feature representation that includes, for example, one of the features might be the score of a standard baseline, like the vector space model baseline. So it will just be like the counts. And another feature might be like the same thing, but only for the title match, and then you could have like URL match and anchor matches and things like that. So they've done this kind of work, but they didn't do supervised learning over the words themselves. They just took these kind of features that kind of summarize the words in various ways and made a kind of low-dimensional feature representation. So what we want to do here is try and learn from these from the words. Now, if you look at methods like latent semantic indexing, that does do what I want. That learns from the words, but it does it in an unsupervised fashion. So the difference here is it's going to be supervised, and we'll show that makes a huge improvement when you look at the generalization of using the metric. If you're training on the metric of interest and testing on it, you're going to see a big difference compared to unsupervised criteria. So let's just go to the details. So these are two of the standard kind of baselines. So the first one at the top, at the top, this is the vector space model one where there's no learning. You just do the valid words. So that lives, your feature representation of the document lives in this d-dimensional space. That's the size of your dictionary, the number of words. And then you're just going to, if you normalize that to unit length vectors, and then you just say this function f here, which measures the map between a query Q and a document D, is just the dot product of those two vectors. Then you've just got the cosine similarity. So, this works. This already gets you quite a way there, actually, which is I mean, in other tasks you don't. I mean, for example, in image recognition, we're going to see later, you don't have as strong features as you do with text. So you can't do these kind of dumb baselines. But for this kind of task, you can. And that already gets you quite a bit way there. But still, there's problems with it. One, it doesn't deal with synonyms at all. Basically, I have an example of this here. Just cut to this. For example, if the query was kitten, vet, and NYC, and the document was cat, veterinarian, and New York, you've got no words shared between the query and document here. So with this vector space model, you just have a zero score, right? So this doesn't deal with synonyms. So that's where your machine learning can help. You could learn these synonyms, for example. So LSI kind of deals with that a bit by basically taking this very high-dimensional vector space of the dictionary and embedding it down to something like, say, 100 dimensions. And you hope then that kind of like your synonyms are basically embedded in the same way, so that then when you do the, say, cosine similarity in that lower dimensional space, you've got a match. Then the vectors aren't orthogonal anymore. And then that's typically learned with a reconstruction kind of objective. So say like you're trying to find a low-dimensional embedding such that if you reconstructed the document you had a small squared loss, something like that. But you're not actually paying attention to matching queries and documents in a supervised way. So for example, at Google, we've got click-through data, right, where people have clicked for a given query on some documents, and you can see this as basically as supervised data. You know that for a given query, people like that document, so you have these pairs. So you basically have the supervised data and you can train on it, and LSI doesn't take advantage of that kind of data. So the kind of models I'm going to suggest to use for this task are, I call them supervised semantic indexing, as opposed to, well, latent semantic indexing is unsupervised, and I also have this polynomial in the front because I'm not going to consider just linear embedding, but also nonlinear ones as well. And so here I'm going to look at kind of the full rank case, and then in the next slide we're going to look at what's wrong with this model and how we can make it low rank and more feasible. So here, the full rank models, we're going to consider, so again we've got this function FQD that matches between the query and document, and we're going to consider a feature space for our query and document where we just concatenate the two vectors together, so that's these d-dimensional vectors where d is the dictionary size, and then we're going to consider all the polynomial terms between words. Okay, so if we just take all the 2-degree terms, that would be like all the possible pairs of words. So, for example, cat and kitten would be one feature, where that's particularly you're interested in cat in the query and kitten in the document. But you could also consider where you have pairs of words in the document or the query alone. But those things won't actually change the matching score much. They'll be more like kind of document quality, sort of page rank things if they're only on the document side. So after we've done that kind of 2-degree term stuff, we would have this kind of model where we basically have now our when parameters are a matrix, which is d by d, and we're considering the ith query term and the jth document term, and then we have a weight wij for that term. Okay, so we're going to have a weight for every possible pair of words, and yeah, we can just write that GTWD. W is the matrix there. And then for the degree 3 terms, you would then have to have, this like 3-dimensional tensor, the same thing. Here I've written it just where I take 2 words from the document and 1 from the query. And then I've also added on the degree 2 model, so it's like degree 2. Now we could just train these kind of models with our supervised data. If we had enough supervised data, we could presumably learn these things. Obviously, we need a lot of it because there's a lot of parameters, right? I mean, even the degree 2 model's got these d² parameters, and then the other one has got the d³, and that's going to present a lot of problems. We're going to need a lot of data. We're going to need a lot of memory to store the parameters, even, and it's probably going to take a long time to train. So these are issues.
Excuse me, capital D is the number of words or in the vocabulary, or is the number of queries in the document?
No, it's the number. It's the dictionary size. The
Dictionary size.
Yeah, words in the vocabulary. So I already sort of showed this slide a little bit, but I was trying to. So here I'm explaining why you want to learn these kind of models at all. And then down on the bottom of the slide I have kind of an explanation of why you would want a degree 3 model compared to a degree 2 model. So it's just a stupid example here where in the query if you had the word jagger and in the document you had the word stones, a degree 2 model could find a weight wij for that particular pair and tell you how good a match that is. But if you had the word stones and gem in the document, so now the document looks more like it's about precious stones and not about the Rolling Stones, you might want to have a different kind of score for that term. Wij would be presumably a lower match, and a degree 2 model can't really kind of, it can't find those triplets directly, right? Because it doesn't have that kind of power. Obviously, yeah, that's going to be hard to learn as well, because there's a huge number of possible triplets. If your training set doesn't cover them, you're not going to learn that. Yeah, and then so the size of these models are pretty ridiculous. You've got like 3 gigabytes or something like that if you had a dictionary size of 30,000 words, which is kind of modest. 14 terabytes if you have like 2.5 million words, which from Wikipedia, say this number because in Wikipedia at the time we did the experiments it was like 2.5 million words in the vocabulary. So if you go over the whole web, then obviously it's going to be way bigger. And then the computation's a little slow as well because you have to do this whole matrix multiplication. Although that's somewhat sparse because the bags are sparse, but still there's a kind of m times n cost where m and n are the number of non-zeros in the query document. Okay, so how can we fix these models? So we want to make them smaller in memory, we want to make them faster, and we want to make them generalize with less training data. So to do that, we do the same trick as LSI, basically, where we have this kind of low-rank models. So what we're going to do is just say that this W matrix, say for the degree 2 model, instead of just learning every single parameter, we're going to replace W with this approximation. It's UTV plus I. So I is the identity. We're going to keep that because it's important. And the reason why it's important is because that's basically, if you only have the identity there, you go back to the vector space models that just do the dot product between the query and document. Right. So we know that's quite good. That's like one of our baselines. So you kind of you need this part. And also, if you don't include that part, if you only have the low rank part, you can't approximate the identity well, right? Because you don't. I mean, that's full rank, so you can't get that big. So here, the U and the V, what are they? Those are parameters for U is for the parameters for the query words, and V are the parameters for document words. So basically, every word in your dictionary is going to have some low-dimensional vector, like a 50 or 100-dimensional vector. But you're going to have 2 of those, one for the query mapping and one for the document mapping. And so then you basically, the match between a query word and a document word is no longer a single entry in the W matrix, right? It's the dot product between the 100-dimensional vectors. And so we want to learn this thing. And we can do the same trick for, degree 3 models. So that's something that LSI doesn't do, as far as I'm aware. So to do that, you need to, this is how we did it. We did this kind of approximation where, so now it's the 3-dimensional tensor. We're going to approximate that element of it with this expression, which is basically just taking the 3 vectors of the 3 words of interest and doing this kind of component-wise multiplication. So it's kind of like a 3-way dot product. So that's how we do the 3 version. And you can kind of look at this kind of thing in a neural network way if you want. I don't know, for some people that sort of helps. So the way that works is, so you can imagine the query coming in on this side and the document coming in on this side, and you have these 2 modules. They're different, and each one of them embeds that larger thing down. So this thing is like 30,000 dimensional or 2 million dimensional. It becomes down to 100 dimensional or something like that by the time you've gone through the 2 modules. And then you do the dot product to get the score. So for the simple like degree 2 case, these modules are just like they're just linear transformations. But in the degree 3 case, for the document module, it's actually something else going on. So this is the expansion of that box. There's actually 2 linear maps, and then it's component-wise product. And that's what comes out of that thing. I don't know if that helps, but neural network people. Yeah, so that's the models we're going to try, and now we just have to train it. So back when I did this work, a lot of people were doing a kind of AUC training where you just kind of just take triplets of a query, a positive document that you know, so this is supervised data, you know that these 2 are paired, and you have a negative document that you know isn't paired with that query. So as soon as you have these triplets, you can try to learn to rank them in the right order. So the D plus and the D minus, you want them to be ranked the right way around. And so you can use this kind of margin-based pinch loss thing to do that. I mean, that's the same thing that is done by other people like Weston. So yeah, we just use that same loss function and we train it with stochastic gradient descent. So we're just sampling these relation and doing a gradient update per relation. And so this we can do very scalably. We can train on millions of such triplets. So prior work, I've mentioned some of these things already about doing SVM kind of learning terrain. Europeans did a lot of work on that, and same with Burgess. And in contrast to those kind of works, I would say we're using the words as features, and then we have these huge feature spaces, and we're trying to find a hidden representation. So in a lot of those works, we're kind of using the small feature spaces with hand-coded features. So then there's also a lot of work on optimizing different loss functions. So basically trying to do smarter things than this ranking loss that I showed you. And yeah, I don't address that in this part of the talk. So yeah, of course, if you had one of these improved loss functions, so for example, you were trying to optimize the top of the ranked list, you could try and use these models, but just change the loss function. And that's what I'm going to do in the second part of the talk. So yeah, let's go to some experiments on Wikipedia. So at the time of doing this, there were around 2 million documents and 25 million links in Wikipedia, which we split into train and test. And the setup that we did was we pick a document from Wikipedia and we kind of say we're going to extract a query from that document. And then we're going to look at all the links from that document and all the other pages that link from that. We're going to say that those are the G pluses, the paired documents to our query. So we're going to consider 2 setups, one where the query is actually a whole document and one where the query is just a few words. And we're going to do that by just sampling some of the words from the document, like at random, just to mimic basically keyword search. The reason we did this was because there wasn't really any publicly available large-scale data set of kind of query document pairs. So we made this kind of proxy. Yeah. So the first thing we did was limit the dictionary to 30,000 words. So we just took the most frequent and threw out the rest. And the reason we did that is so that we could compare to if we don't do the low rank learning. Like if we just have a full rank W matrix and we call that like a margin ranking, etc. So then you have this like D squared, 30,000 squared parameters. And so our model that I introduced to you for degree 2 and degree 3 is here. And then we have several other baselines. We have what I call, well, it's just written TF-IDF there. This is just a TF-IDF normalized, bag of words and cosine similarity. And query expansion, try that because it's actually working better anyway. And LSI. And it's important to mix LSI with the vector space model, like TF-IDF otherwise. There's a lot actually. So we have 3 different kind of metrics here: precision of 10, and average precision. And the rank loss is the percentage of these pairs that I showed that we were training on over the one-way round test time. So naturally, I mean, well, this is the thing we're training on. So, on the training set you would hope we're lower, but we're also lower on tests, and then the other metrics actually follow quite nicely with the same trend. I mean, when this one goes down, this one's going up. So yeah, you get this fairly substantial improvement over like no learning at all, TF-IDF, and of LSI to didn't actually bring that much in this case. So so basically, I mean, these 2 models here are like same models, just trained differently.
So for something simple like TF-IDF, do you try bag manuals? It's not the same version of Tsunami, but you have sort of local context, sort of providing.
Didn't try it, but I didn't know that there were big wins from that. I didn't know that there were big wins from that in general. But,
computational / space complexity of this isn't the capable filling substantially harder.
No, well, you've got the number of parameters here actually. So you've got D squared versus. So here I have a 200-dimensional embedding space for the query and the document. So this is why this is 400 the number of parameters. And this one is also 200, so you have 3 embeddings now, so it's 600. So no, it's not a big difference.
Question. So where does your negative example document come from?
Oh yeah, they're just totally random. Yeah, also not great, but that's the proxy.
This problem just asks how would that topic and
Mixture model?
topic and something like, that apply.
Oh, okay. So instead of LSI, like a more complicated version of LSI.
Yeah, language model based.
Yeah. I mean, obviously I haven't tried it, otherwise it's useless.
I mean, I know language models sometimes perform very well. Just curious.
I would expect it to be, I mean, something like PLSA or something like that would be very similar to this, I think. And basically, doesn't bring much, and the reason why is because it's not supervised. Now there are sort of supervised versions more recently that David Bly has made, but the one I saw, maybe he's done something more recently, still couldn't be applied directly to this because the supervised part that he added on was a document labeling. It wasn't a query document retrieval matching.
Excuse me, when you say LSI, you mean BLSI or just saying, the usual LSI?
No, this one's usual. But
Okay.
I was,
Okay.
so
I'm just asking if you've used any language modeling approach.
No.
No?
So I suppose your optimization problem is really non-convex.
Right.
Do you actually do multiple research and learning? This is just a simple reason. Do any smart initialization?
I mean, when you say really non-convex,
Well,
I don't know
maybe
about
not.
the really.
Yeah. Okay, I'm
It
sorry.
is
Non-convex.
Actually, I don't find big problems with that. I didn't do any restarts. So it does have a random initialization of the weights, and then you train. But you could consider sequentially convex problems where you train like the left-hand side embedding and then the right-hand side embedding, and both of those will be convex problems. So you could do that, but I don't know if it ends up better. I tried a bit.
So once you have K equals to, you run this W, which is sort of like a word similarity for pairs of words, something like that. To go from K equals 2 to 3, right, you sort of have that information already in 2, which just translates, right? And so if you had some kind of like spectral,
I mean,
if you had some
you
spectral,
have some of the information, but you still couldn't.
well, if you know that, you know, cat is kitten and kitten is kitty, right? Then you know that cat is kitty, right? So
Yeah, but if you had a triple where there were kind of, it was a negative example if they're both there, but they're positive examples on their own. This you can't do. So, but I agree, I think most of the things you could probably
So I think if you took the two-dimensional case and then you applied some spectral clustering style approach, you get that to a representation which is taking into account all these transitive dimensions, right? That you can get away
So
from
we're
that.
already doing something like that, right? We're already learning this low-dimensional embedding. So spectral clustering also learns low
Right, but it learns a low-dimensional embedding that can follow the structure of the graph specified by your W d by dw for two-dimensional.
Oh, you want to learn the full rank one first, and then do spectral.
Right,
Oh, okay.
right.
The
And
problem
that
with the
avoids
full
that.
rank
avoids
one
K
is
equals
this
3.
thing is just really massive.
Well, you did it.
Only because I limited the dictionary size to 30,000. So in the next experiment, I used all the dictionary.
And then it goes over.
I couldn't do it. I couldn't do this experiment, so I didn't put it in. I used like this other thing called hash kernels by John Langford, which basically kind of has a random hash of the pairs into a lower dimensional matrix, so that you can still kind of use all the word pairs, but you don't blow up your memory. But this thing, I mean, it kind of works actually, but our approach here was working better than that. And so these numbers are directly comparable to the numbers before, actually. So you can see the improvement you get from using the extra words in the dictionary. And well, CF5DF actually goes from 1.62% to 0.846. So that is a big win. And these ones go down a bit, but they've already shifted quite a lot from the 30,000.
So if you say that you can do the left-hand side embedding, the right-hand side embedding independently.
Well, I didn't say independently. I meant you can train it by fixing one side, yeah, and then sort of training the other, and then fixing that one, training
Because
that.
because that will give you two different subspaces which you can't do the same. Like if you do it independently, can you?
I don't know how to do it. I mean, I was saying you kind of have to keep going down and down and down, like training like that. I don't know what it is. Yeah, I don't know how that's to do. I'd like to know new ways of training it, but ways of training it fast. Cool if I could do it in parallel and stuff like that. It's just another. This is just a scatter plot of the average precisions for various queries, comparing our model SSI to TF5EF, so the vector space thing, and to LSI. So you can see the wins are pretty much across the board. And then same kind of experiments, but the query now isn't a whole document, it's just a few words. So either 5 randomly sampled words, 10 randomly sampled words, or 20 randomly sampled words. And the less words you have, the harder the cognitive ranking. So the metrics are worse, but you get the same trend between the models. And we also did another experiment with cross-language retrieval. So we took like the Japanese documents in Wikipedia, and then because it's like marked up, you can find the English version of the page.
Use the number of parameters in various algorithms. There's a key factor in there, which I think I don't know how to end up.
In which one?
Well, in the SSI stuff, isn't it a low-dimensional embedding, which means you're learning in the
Yes.
low-dimensional space?
Yeah, so every word has a low-dimensional vector, like in this case, a 200-dimensional vector. Okay, so every word in dictionary, and the D here is the dictionary size. So that's it. That's the parameters. And I mean, this is. So this is this thing. So this thing was D by D matrix, right? And these two are like D by 200. Oh, yeah, cross-language retrieval, similar experiment. So there's Japanese query now and English targets. So that's a bit more interesting because a lot of the vector space models don't work right now. You can't just look at the count of the number of matches between query and document because they're in different languages. So we made a baseline where we translated the query first and then do the counts. So that's that model there. And then you can do the same thing for LSI. And there's a method called CL-LSI as well, where it's a bit smarter, where you basically take the paired documents in the two languages and run the LSI on that. But for our model, that kind of data presents no problem. It's exactly the same thing for it. I mean, during training, you've got query vectors and document vectors, and you're trying to find this low-dimensional space where they match. So yeah, we compared doing our model like in the natural way for this task to doing our model where you sort of do the translation first with the query and then it's all in English. And you actually get an improvement from doing it directly on the Japanese and the English. So presumably because the translation is making mistakes, and then you can't correct that afterwards.
So what's the best you could do on P10? Is it 0.1 now? Is there only one correct match? Or?
No, because it's the same setup as before. It's like links, so I don't know the exact numbers.
So I guess now there is a directly corresponding page, and there are also things.
Yeah, but actually, the directly corresponding page, we in the setup we threw it away, and we only kept the links, and those were the ones that did. You could look at what's inside your W matrix. You can basically see, like large values of Wij will show you which pairs of words have a high score, and so kitten and cat has a high score, and Beatles and McCartney has a high score, things like that. But you can see these kind of lists in unsupervised kind of models as well. So I don't know how much they tell you. I mean, in the end, we're interested in the precision metrics. So yeah, so that's the first part of the talk. I think it took longer than I thought. So yeah, I'm going to quickly through the second one. Yeah, let me just go to the second one. So in the second one, we're going to use the same kind of models, but we're going to do image annotation. So what is image annotation? Well, for us, it's if we have like an image like this, and we have a list of possible annotations. Like, let's suppose we have a huge list, like 100,000 possible annotations. Then we want to have a method that ranks that list such that, so here it's a rank list such that the top ones in the list are most likely to be correct. So yeah, these are actual annotations.
Jay-Z actually never says
so I mean, obviously there's already many methods to do this task as well. So we're looking for, I mean, our goal is to try and improve precision over some existing baselines, but we also want a fast model and one that doesn't take up too much memory as well. And those kind of models that I talked about in the first part of the talk, we want to satisfy those demands. So now we have to see do they perform well, basically. So the kind of data sets we're looking at here are a publicly available one, ImageNet. Actually, it's bigger now. It's, I think it might have reached 10 million images now. But it's bigger? Oh, okay. how big is it now?
12 to 14.
Okay, cool. But yeah, I guess this is much more than a year ago. It was much more, but still a few million. And then we have like an internal data set which is called Web here, where we took a subset of over 10 million images. And so for ImageNet we have around 16,000 possible annotations. Text annotations, and for the web data set we have 110,000. So apologies to you as well for this part of the talk. Yeah, so we're going to try and find a small model that works well. So if you use something like one versus the rest, like one versus the rest SVMs or something like that, which is a common approach, you've got a problem when you have 110,000 annotations, because that's 110,000 SVMs, and depending on your feature representation, the representation we use in this work is like a 10,000 dimensional bag of terms. You've actually got a lot of models to learn. That's a lot of memory. So that's that I think that's where I'm getting my 8 gigabyte number from there. Whereas if you use these kind of low rank models that I just talked about, you'd be more in that 80 megabyte range. And you're also a bit faster. So 0.17 seconds versus 0.5 seconds, not including the feature extraction, which they both have to do. So the new thing in this part of the talk is that we're going to show how to kind of optimize the top of the rank list and not just use that ABC training that we did in the first part. So just a picture of kind of what the algorithm's doing is we've got this low dimensional embedding space, but now we don't just have words, we have these images, and they're going to go through some transformation phi, and they're going to land in this low dimensional space. And then we're basically going to rank the annotations by how far away. So all the text annotations also live in this space, and we're going to see how far away they are. And we're going to rank them according to that. And so we want to learn basically jointly this mapping file that embeds the images and the ones that embed the annotations such that precision of K is optimized. So that the closest K here contain the true annotations or annotation. So this looks pretty much like the first part of the talk, that the representation is a linear embedding. So as I said, we're going to have a 10,000 dimensional feature representation for images, and we're just going to have a 10,000 by 100, say, matrix. So there's going to be a linear mapping down to the dimensional embedding space that I've shown here. So that's just a linear map for the images. For the text, it's the same as the previous part of the talk. That every text annotation is going to have one vector. So this is going to have a 100-dimensional vector. I suppose slight difference is that actually, so something like Eiffel Tower here, because it's a whole annotation, will have a 100-dimensional vector. I don't break it into the back of the words. And then we just do the dot product after doing the embedding to score the similarity between the image and the text annotation. So this slide is just to convince you that the kind of training I was doing in the first part of the talk is suboptimal. So imagine you have like two functions, and you have two training examples. So, and you want to, in your training, you're trying to choose one of these two functions. So the first function, it ranks, for the first training example, it gets the true label ranked first. But for the second example, it gets the true label ranked 101st. Okay? And the second function, it ranks the true label in the two examples 50th and 52nd. Now, the interesting thing is that they both then have like 100 Oracle violations. These are negative labels that are ranked higher than the true label. So this kind of AUC loss that just counts the number of violations likes these two functions equally. But we might like the first function more because basically it gets one of the examples right, it gets the other one wrong. Whereas the other function gets both of the examples wrong, basically. I mean, as soon as it's down below, the first 20 things on the list, then no one's going to look at it, basically. I mean, depending on what you're going to do with this actual model afterwards. You can imagine a UI where you take a photo and then it shows like the top 10 annotations or something like that. So Nicolas Rasunier, who's was my collaborator on this work, in a paper at ICML 09 came up with a kind of a family of loss functions that fixes this problem from the last slide. So a little bit complicated looking, but so what it does is basically it says that the error of a given example and your current function is measured by finding the rank of the true label, so that's where it is in the list, and then transforming that number with some function L, and that L tells you basically the penalty that you get from that rank. And then if you choose this L transformation in a smart way, basically you can kind of prefer the top part of the list. If you make L in another way, you basically go back to the AUC loss you don't prefer. So basically, as you switch this L, you can change how much effort you put into optimizing the top of the list. So the way he wrote that was basically he said that L is some of these alpha J, which are just fixed parameters, things you fix in advance before training, and you sum. So for a given rank K, you sum up to the kth one. And so basically, if you make them those alpha constant, so you're just kind of counting the number of violations, that's when you get the ABC. But if you make the first ones larger, so you take something like alpha J equals 1 over J, something like that, then basically you get this decaying kind of sequence, and you're going to pay more attention to the top list. So, for example, with alpha J equals 1 over J, if we look back at the example of those two functions I was talking about on the previous slide, you get those values of L. So function 1 gets a value of 5, roughly 5, and function 2 gets a value of roughly 9. So you prefer, because you're minimizing the loss, you prefer the first function. So it's doing the right thing here. So so we're going to try and basically use that with our embedding model. Unfortunately, it's a little bit tricky because what we need is to basically, when we get a new image that we're training on, if we're doing kind of stochastic gradient descent, we've got a new image, we know the true label, but to compute this L function that he wrote, you need to know the rank of the true label. So that means you have to go and rank all of the possible annotations. And if we've got 100,000 of these things, that's already kind of costly, even on a single example. And that has to be really fast because we need to do millions of these updates on these examples. So so just counting that number of violations there, that's a problem. So basically, we have a trick to approximate that rank, and the trick is as follows. We just instead of going through all the negative examples, we pick a random negative example, and we look to see its rank compared to the true label. So is it before or after the true label? If it's a violating label, then we stop and we say the rank is estimated to be the number of possible labels divided by the number of times I sampled. If it's not violating, you pick another random one, and you keep going until you find one, and then that value n there is the number of trials it took for you to find one. So basically, intuitively, if there's a lot of violating labels, then randomly as you pick one, you're going to find one quickly, right? So then the rank is going to be high, right? Where if it's hard to find one, the rank's going to be low. So it's not exactly correct, unfortunately, so actually you can look in terms of expectation what this trick does, and we want it to be on this diagonal, like this would be the true rank, and this is our estimate of the rank, but we get this dotted line actually. And that's in terms of expectation. And in terms of sampling individual points, because that's what we're doing when we're doing our stochastic gradient descent. Again, this would be the value of L, the actual loss, and this is the loss that we calculate. We want to be on the diagonal, we kind of dotted all over the place, roughly following the trend. So it's not quite right, but it's much faster. So that's the trick. So then we end up with this basically pseudocode for training, which I just basically explained already. You pick a random labeled example for your stochastic gradient descent. You keep picking random annotations until you find a violating example and you do the gradient update. You just keep repeating. So So I guess it looks a bit like the perceptron in a way, apart from the peak. And then when you do find it, then you're doing an update weighted by the loss. I mean that corresponds to the loss, the OWPC loss that Nicola designed. So let's skip this slide and I'll just go to the talking about the approaches I'm going to compare to in the experiments. So yeah, basically I already talked about one versus rest. That's the standard baseline. We also compared to something called Pamier, which is basically a full rank model where you, like in the first part of the talk, where you have this matrix W and you train it with AUC. That was done by Rogier and Bengier. Alright. And we also compared to approximate Neurosnova. So, well, related work is basically, I already talked about these kind of related text works. And yeah. Do I need to talk about feature representation? I'll skip that. I mean, this is like basically the standard kind of thing that people do with images, where you try and represent them as a bag of terms. So to do that, you kind of segment the various scales, and you do like color and edge histograms, and you run k-means. Say in this case with 10,000 centers, and then basically you could just have a 10,000 dimensional vector, which is your histogram of counts of how many parts of your image go into those bins. So it's not necessarily state of the art, but it's kind of standard feature representation. Yeah, so then we can go to the results. So this is on the two data sets that I showed at the beginning. And we have different metrics here. We have precision at 1, precision at 10. I will talk about this one actually in mean precision. I just skipped this over. And yeah, so immediately you can see they're all kind of pretty bad. Like, precision of 1 or 4% means, we're kind of getting the annotation right at the top of the list, like 4% at the top. So, although they're bad, our method is called the Wasabi here. It's like web scale annotation by image embedding. Doesn't matter. At least it's better than the other approaches, but they're all kind of bad. So, yeah, one reason that they're bad actually is this is a kind of worst case measure, because, for example, on the web images, you have 100,000 annotations, but some of them are very similar. So, like here, you saw that we have like Barrett Obama, Barrett Hussein Obama, and things like this. So if you don't get the right one of these at the top, you don't get it right, precision at 1. So some of the thing we're suffering from is actually from that. I think it's probably more in the range of like 20% in reality that are relevant at the time. Yeah, so we're doing better, but why are we doing better? And actually most of it's coming from this optimizing the precision K that we're doing. It's not from the low dimensional model part. So I have another table to show that. So here I'm basically comparing doing the AUC loss, so we don't optimize the precision of K, and this thing which we call the warp loss, so that's where we do optimize the precision of K. So this is yeah. So basically, whichever model we take, a full rank model here, or in embedding model here, you always see this improvement when you optimize the precision of train. So that's good. And yeah, this is another graph that kind of shows why we had to do the approximate sampling to measure the rank. Basically, if we don't do that, this is number of hours versus length of test precision. If we do like the exact computation of the rank, we're basically down here. We haven't learned anything after 35 hours. Whereas if you do the approximate rank, it's not correct. You're up there. So you're doing much better for that amount of time. Presumably, if you keep running this thing, eventually it looks good. I don't know how long it takes. And then the middle curve is when you just do the AUC training, not the precision K training. So this is converged quickly, but it's already much, so not as good generalization. And I have some test time and memory constraint here. So exact nearest neighbor is going to take you a huge amount of time. This is basically on the whole test, which is millions of points. Basically, I already talked about this time. You're looking at 0.17 seconds on the web data for the sampling. Something like that. And this 82 megabytes versus some number of gigabytes for point versus Weston. It's just something that shows if you change the dimensionality of the embedding, you don't get, it's fairly invariant to that, I would say, although 100 is a little worse than the others. We had another trick here where we tried to build an ensemble. So we basically trained like 3 of these models, like independently. They're the same except the initial condition, like the random initialization of the parameters is different. And then if you basically put them together, we were surprised actually by how big an improvement you get from that. Like you go from 4% to 6% P of 1, which seems pretty big.
How do you put them together?
Just additive. Voice is equivalent to concatenating the vectors together.
You don't do any meta learning.
No, just equal weight. We tried something else where we took a different set of features that's supposed to be better than the bag of visual terms. So it's basically an ensemble of features now rather than models. I won't talk about all the details of it. But basically there's a whole bunch of different features, concatenate them all together, use kernel PCA to make it lower dimensional, and then train on that. And you get another improvement because basically these features are better. So to compare, that was the results we had with the bag of visual terms. 6% if we had the ensemble and 4% if we don't. And with these new features, we can go up to 9% without the ensemble and 10%. So now the numbers are getting a bit more reasonable. But this sort of goes to show really that the thing we're working on here, like optimizing precision K and optimizing the models, I don't think it's the most important thing for image annotation research. You should be working on the features that happened before that. It's going to bring you much more wins probably, although there's a whole community working on that. I don't know how much further they've got so far. This is just another thing to show after you've learned the annotations, you can look at which ones are are close to each other, similar to what I showed you in the first part of the talk. You can see some nice things, where it finds David Beckham close to other football players, and stuff like that. These are just some example annotations system. And yeah, taken up too much of your time already, so I think I'll finish with that.
You actually try to do this unsupervised deep learning? Because I know you're trying to some other
For the images,
well, either one.
I mean, I kind of got these results and then I tried to beat them. I tried to do some non-linear stuff, and yeah, not exactly deep learning, but some things around that kind of thing. I haven't managed to get any better. So,
My second question was.
but let me just say a bit more. But the problem is, like, these like deep convolutional nets, they're really slow to train, and I've got like 100,000 annotations and a huge number of images, so that's kind of my bottleneck with those models, is training.
And also, now that you're at Google, and you try to look at actual queries and documents, to do that instead of.
Well, I mean, these are kind of queries and just the documents are images. So I have worked on this. I've been working on Google Music as well. And I've looked at trying to use these models there. So there you're embedding like the music, the audio, and well, also text, potentially like the genres and the artist names, the color names and stuff like that. Well, MSCCs we've tried, and then this is other people with SAIs.
But then you make some kind of bag of, what beats, I don't know, what is, in other words, are you just tiling the MSCC?
I don't think so. I mean, basically someone gave me those features and I used them. But there's several papers published by those people like Dick Lyon and stuff, and you can see what they do for these other papers.
Any other questions?
Yeah, for the first part of the talk, I think you should talk to the team here, which is about discriminative language modeling, because apparently there is some connection there. So essentially, for each query, you would like to rank all the documents which are relevant higher than those which are irrelevant. So you have a language model that you train discriminatively, and then essentially the probability of the relevant documents will be higher than the probability of the irrelevant documents.
Okay.
And we have the techniques to do that.
Okay. Well, that sounds pretty similar.
We're on the hook for lunch, so we're going to do lunch.
Okay, so you will talk.